2019 higher tier Year 11 double award paper. So I'm going to run through this. There's your formula sheet. First question is all about radiation and half-life. So there's a practical being done with 200 coins, and it's all about pattern spotting here. So they remove 0, so you've got 200 remaining. They remove 104, so there's 96 remaining. You can see that the pattern here, that they keep subtracting from each other. So it's about recognizing the pattern there for 1 mark to fill in the blanks. After 2 throws, the number of coins remaining was 51. How many coins would you have expected to remain? Well, it would be 50, because that's kind of what we predict. So 200 will halve to 100, will halve to 50, but there was 51 remaining. After how many throws would the number remaining coins fall to 1/8? So we're going to do a quick table. It's only worth a mark, but we're going to do a quick table. So we start with 0, 0, and we don't really have to worry about the time, because we can see that 0 half-lives, 1 half-life, 2 half-life, 3 half-life. I don't have to fill in this middle bit, so I just go take it from 1/1, which is what we always start with, to a half, to a quarter, to an eighth. Let's have to 3 half-lives. So how many throws? Carbon-14 is blah, blah, blah. So this looks like a nuclear equation. So I got 14 equals 14 plus 0. 6 equals something plus -1. It's got to be 7 there. And that's 2 marks. So you get a mark for the 14, a mark for the 7, which is quite generous there. Then we've got this last part of the question is quite hard, but we've got a little bit to do with half-life. So sample of 80 million carbon nuclei decays into nitrogen and so on. So let's have a look at what the question wants us to do. Complete the table. And again, it is pattern spot. And we start with 0, we got 800. Sorry, they take away 0, you get 800. And they start each time again. That's the important thing to read from the question, that every time they start from 800. So we're going to be taking away this number from 800 every time. So just be aware of that in the question there. It's all about reading. So they're going to start with 800 every time. And then, so you're going to plot these now on the graph, the ones that's been done for you, I think. It's been a while since I did this, but I think we're going to do those. So we plot them on a graph. There's the graph. Where's the graph? Back up there. I have done this all wrong, haven't I? So when we plot these now, make sure your line is better than mine. And I did it in pen. You're not going to get marks for that. See, they call that where the curve's quite hairy, they say. But it's just obviously not a straight curve there. So make sure your curve is nice for the 3 marks and your plotting is accurate. So we've done that. So state the meaning of the term half-life. So it's the time taken for a radioisotope's activity to mass, for its mass or activity to decay by half. Use a graph to determine the half-life of carbon-14. So we've got to go back to the graph. So the graph shows that the half-life of carbon-14. So it's going to be the dots, the crosses, the one we've just done. You can see the half-life 800 down to 400. It's the same half-life from both anyway. So we half the 800 to 400, bring it down, and it's 6 because each square is 0.5. And then this is a bit of a minging question, but it's really about recognizing that the curve from 80 million will be the same as 80 million. So it's just a factor of 10 there, I guess. So we're going to use the graph to find how long it took to fall from 80 to 76, because it decays by 6 million, and then we're going to see if that statement's true. So 80 minus 6 is 76 million. So if I go back to the graph, and we're going to use the 800 down to 760, because we're going to use that, the factors of 10. You can see that it's only got 1 square. So if I bring that back down, the 1 square is worth 0.5, and these are in thousands of years, so that's 500 years. So it reckoned up there that it was 2,000 years, which is, the claim's not correct because it's only 500 years. Not a very nice question, that one. Not a lot of people got that right in the main exam. Question 2 then, safety of cars. So what's Newton's third law? Object A exerts a force on object B, then B exerts equal and opposite force back on A. How does this relate to the car on the wall? And you're just replacing words for the wall now. So the wall applies force on the car, collision, the car applies equal and opposite force back on the wall. So with this one now, it's asking us to do, what does it want? This will calculate the mean resultant force. So in order to get force, F equals ma, it looks like we need some sort of acceleration, which we do. So to get the acceleration is change over velocity over time. So I'm going to use my graph from the first page now to pick out some of these values. So the change in speed was 0 and 15. So it's going to be 15. And then, I don't know why I've put u as 5 there. So that's going to be 15. So that's a bit of a mistake. And then the time it takes, as we can tell from the graph, is 0.2. And then we're looking at this scale, and that comes to 0.28. So I can find the acceleration from that, or deceleration, because it comes out to minus 535.7 meters per second squared. And I'm going to use that now with the mass to calculate the force, F equals ma. It comes out to 46,000 newtons. Use the graph opposite to explain whether the resultant force is constant during the collision. I've said it's not constant because the gradient is not constant. Because it's a curve, it's the force is not constant. It's decelerating at an increasing rate, so the force must be increasing if it's decelerating at an increasing rate. Explain in terms of the work done how a crumple zone works. The crumple zone is going to increase the distance all the time, we can say, to stop. Therefore, it's decreasing the force. And there's ways you can show that. You can see that I've increased the force there, and the acceleration there's got to go up. If I decrease the force, the acceleration's got to come down. If you keep the mass the same, so it's gonna decrease that time, or the distance, when you plug that back in to the distance speed time. Okay. But no, you don't have to show that. You just need to. I think the big thing from this is knowing that a crumple zone increases the distance all the time before you hit the wall. Therefore, it's going to decrease that force. This one then is the 6 marker on a life cycle of a star. So I'm not going to talk through this too much because we would have done this loads in class. But I wouldn't lay it out like this, but you can certainly put it in bullet points. Bullet points is not going to get you the 6 marks. It will get you 5 marks, but bullet points makes it so easy and clear for the examiner to mark. We're talking about forces. We're talking about reactions, okay? And we're talking about each stage. You're probably going to get maybe 1 mark for listing the stages and recognizing that it's a high mass star, so it's a big star. So you're going to get that red supergiant into a supernova and then either a black hole or neutron star. And then we're going to talk about each of these stages in terms of force and fusion. A nice little question here for 3 marks then. You need to know that, you need to tell them that it's the first 4 planets are rocky and the last 4 are gas. And gravity is strong enough to pull the rock together. That's how they originated. So it's just gas and dust collapsing under gravity. So for this one is back on nuclear, radiation, and outline the dangers to people's health for each alpha, beta, and gamma. So I've said alpha presents no danger because it cannot penetrate the skin. But if it did, if we inhaled alpha, or if we consumed it, or if it was injected, then it would be the most dangerous because it is the most ionizing. So it'll do the most damage to our cells and mutate them and mutate the DNA in our cells. Beta and gamma are able to penetrate the skin, but gamma is more ionizing, so I guess it's less healthy for us to have beta, sorry. This is why they often use gamma as tracers and make sure it's a short half-life with a tracer. So we've got some information here. This is just recognizing now Recognizing that the low-level waste, oops, didn't want to do that, in the UK. So we've got 30,000 there, meters cubed, and the number of power stations is 15. So for every power station, really, we're getting 2007 meters cubed waste. For France, it's got 58 stations, so 58 stations there for France, but it's got waste of 87,000. So even though there's more power stations, there's more waste, but there's less waste per power station there. So the UK produces a lot more waste per factory than France. So a bit of a numeracy question there. And then a bit more information, and I'm expecting you to read this information, obviously, and not just copy these answers in, because a lot of this is from there and you don't have to memorize. So the presence of volcanoes creates a danger for leakage from the containers. That's one of the reasons for that long-term storage waste there. And then you're going to use the table to recognize that large populations in a small area for the UK, therefore less area available for storage sites. Okay, that's the 2 marks there. The UK opened first nuclear power station, blah, blah, blah. So why is the costs changed? Well, low fuel costs, probably at the time when it opened, but they now need to include the cost of storing the waste and decommissioning costs. So, and obviously the costs that it takes to keep that station running and the repairing. So it's not going to be as cheap as they first thought. And that's your 2 marks there. And then this one, other than what we've said, what else, how else can we get rid of nuclear waste? The big 2 really, sent into space. The advantage is gone from Earth, but if it explodes and it's back to Earth, and that's going to be disaster. And then the deep sea, storing in the deep sea, it's away from human activity, but tsunamis and earthquakes, possible danger of leakage there for 2 marks. Last 4 pages then, and we've got question 5 on springs. So a lot of numeracy going on in this question. So we're looking for, now, I want you to recognize that at least 1.2 newtons. So these are going to all at least 1.2 newtons. Can't be any of these. Can't be spring A or spring B. And close to extension of 14. Well, you can see that we've got here in the table, we've got the unstretched length, the original length, and then we've got the maximum length to which is stretched. So if you take 9.524 away from 23.495, which I did, you get close to 14 mil. So it's kind of a trial and error there. You kind of, I know 20 minus 1 is nowhere near 14. I know 14 minus 1 is, more like, well, that's more like 2, so that's going to be around about 12. So that's why I picked this one. Went for that one straight away. So spring D. Express the spring constant for spring A in the standard units of Newton per meter, and the key there is per meter. So usually, and I've got here, usually because we use the Be Smart Mate, Stop Being Dumb, and because we're going from a millimeter to a meter, we'd usually go from small to big, which we divide. But in this case, let me just show you what's happening. Because it's a per meter, what we're saying is we got 0.17 newtons for every 1 millimeter. Therefore, we need to times that by 1,000 now, because it's reciprocal. So it's going to be 170 newton meters. Again, a tough question, but this is question 5 now. A couple of easy ones coming up though, so they will try and catch you at the beginning of the questions, make you think, but you've got to keep going and looking for the easy marks. Okay, this is another one that includes, and it's only worth 3 marks. There's been 2 of these now on this paper. They seem to be getting less generous with these combined equation. Usually you'd recognize it from 4 marks, but now this is 3 marks. It's still using 2 equations. So, looks like we want the energy stored, and if we're dealing with a spring, the only equation we can get from the front of the book with energy work done, remember work done is energy, is going to be half Fx. So your force and your extension there, which when it comes to springs. First of all, though, we need to find that force by using the Hooke's law equation, F equals Kx, which is your spring constant times your extension. So to do that, I've used the information from the chart. So it wants it for, let me just check now which, it wants it for spring C, look. So I'm going to go over and look at all the information from spring C. So I can see that it's got a spring constant of 0.12, which we know now per newtons per meter is going to be times by 1,000 there. And then we're looking for the extension. So that's what I've done there. So I've got the extension, and again, I've converted that from millimeters to meters. So we're dealing with not very nice numbers here. So when I put the spring constant, which is 120 now, because I've multiplied that by 1,000, times my extension, is going to give me a force of 1.284 newtons. Now that I know my force, I can use now to see my work done, or the energy stored. And half Fx, okay, again from the front page. So 0.5 is my half, 1.284 is my force, and then my extension. And once I know, I can come out with 0. And that's my joules there. Okay, just checking. We're going to use that now to calculate the height by using, because it's giving us gravity, and that's a big clue that you're going to use potential energy now equals mass, gravity, height. It wants the height, so I'm going to use the height. I need to rearrange for height, which is H is going to give me the energy over the mg. Okay, you could have multiplied it out or done the calculation out. I've arranged this so it'd be nice and easy for you to see. So I've got my energy from up here that I calculated, and I've got the mass and the gravity. Mass that I got from 15 grams up here. It did say, I think, it said 15 grams somewhere. I'm sure it did. Oh, there it is. I've underlined it there. Okay. So, and that's how I come up with that answer. So I hope you've got, oh, another page yet. There's me. Oh, yeah, I'm nowhere near done yet. So it looks like this data logger now has picked up some data from velocity and time. So it's a velocity time graph. So if you're looking for the distance, we know it's the area under a graph. And I think that's where I've gone with this. So let's compare it to the height of what we just worked out, which was 0.04, I'm sure. Let me just check. Yep. And then, so I'm going to take the area under the graph, which is 0.9 times 0.9 times the half. And that comes to 0.0405, which is different from that. And then it's going to go on to ask us some questions on accuracy and things like that. Explain how the height reached by the ball is different than theoretical height. Well, some of the energy is lost as heat as the spring retracts. Probably sound as well. And then suggest one change that can be made. You can choose a spring that has a bigger extension or a stiffness to kind of extend our experiment and to get a greater height. Okay, that is that. As you can hear by my voice, I'm very tired. So I hope this has been beneficial to you. And thanks for watching.